An interesting number problem to look at today. We're going to venture into the world of modular arithmetic. We're going to build up from small cases to bigger ones and talk about that as a problem-solving technique. And we'll even touch on an idea called entropy that shows up more often in like an engineering context, but is definitely a good way to describe what it is that's happening with the problem that we're looking at. So let's take a look. The problem statement this time around, a lot more straightforward than some of the other ones that we've looked at. We're just going to answer the question, when are the digits of a number squared small? And so what do we mean by small? Well, we could pick any threshold really that we wanted to. It turns out that a good starting place though is to look for numbers where all of the digits, when you square the number, is less than or equal to 4. So that's where we're going to start, and then we're actually going to restrict that when we get to some larger numbers, just because we end up with way too many cases when we're looking at larger numbers that we're squaring. So if you think about the small numbers, right, the one-digit numbers, well, there aren't really any surprises, right? 1 squared is 1, 2 squared is 4. Those both have digits all less than 4. There's only one digit there. But then as you proceed, you continue to get numbers that all have digits bigger than 4. But what I am going to do is I'm going to list down the numbers here real quick, and we're going to write down their squares because we're going to notice a couple of really important things. And this is the kind of the motivation for starting with zero-digit numbers, or sorry, with one-digit numbers, right? And so as we look at these squares, a couple of patterns emerge, okay? The first thing that we notice is some interesting behavior with the final digit, okay? So we see that kind of at the lower range of values, we have smaller ones digits, right? And then 9, 6, 5, 6, 9. Oh, look, that's a pattern, right? And then if we keep going, it actually turns out that we see the reverse of that pattern continue to emerge, right? And so we're really going to be interested in looking at numbers as we go here that either end with an 8 or a 9 or end with a 0, a 1, or a 2. And the reason why that's relevant is because if I take any number, let's say 34, right, and I square that number, well, it doesn't really matter what the beginning of that number is because the last digit is going to be a 6. If you think about long multiplication, right, so if I multiply 34 by 34, when I multiply this, I do 4 times 4 is 6, right? You've done this. You carry the 1. You've done this probably in elementary school maybe even. 4 times 3 is 12, plus 1 is 13. And the main point that I want to highlight, though, is that when we do the other rows, we put a 0 here, right? And if we were doing larger numbers, we would put successive zeros at the tail end. And so you see that this 6 is always going to come along for the ride. And so that's kind of like the long multiplication justification for it. But really, it comes from the fact that the only way that you get something in the ones place is when you multiply the ones place by the ones place, because otherwise you're going to be carrying extra zeros along for the ride. Okay, and so we know that no matter how many digits we're talking about, if we're cutting off our threshold at 4 or lower, the number is going to have to end in a 0, 1, 2, 8, or 9. Another thing that shows up is that we notice that after about this point right here, all of the numbers are going to not suit our criteria. And the reason for that is that either the last digit or the first digit is going to be too big. And the real cutoff, right, is all numbers greater than 44, right? Because if you're bigger than 44, you're kind of in two cases. Either the trailing digits are bigger, right? And that's going to be the case for 45 up through 49. But then once you hit 50, every number between 50 and 100, so up to 99, is going to start with a number that's bigger than 4. And so we're not interested in any of the numbers that follow that. And we'll see that pattern emerge multiple times as we dig into all of our different bigger cases. So this is the reason why we start with small numbers, right? Because we start to create these building blocks that we can draw conclusions off of that will be helpful in the cases that have more and more cases, right? There are only 10 one-digit numbers if you include 0. That number grows really quickly, right? There are 90 two-digit numbers, there are 900 three-digit numbers, 9,000 four-digit numbers, and so on. So this is going to get a lot more complicated as we keep going. So we mentioned earlier that we had kind of two criteria that we discovered along the way. The first was that the number was going to end in 0, 1, 2, 8, or 9, if we're looking for all of the digits when we square the number to be less than or equal to 4. And so I just want to introduce some notation here. A lot of times mathematicians will put an over bar over the top of the number to indicate that A and B are representing the digits. If I just write AB down, most people would interpret that as A times B, okay? If I wanted to convert this into a formula, though, it would be 10 times A plus B. And the reason why is that we have 10 A's, right? Our tens place is the A value, and then we have B1s, okay? And we could extend this pattern to a larger number. Oftentimes you'll see people use like A1, A2, A3, A4 to represent a 4-digit number rather than using successive letters of the alphabet, but I think A and B just is a little bit clearer to track with what's going on, okay? So let's start breaking down some cases, okay? And so the first thing that I'm going to look at is the case where we have A0, okay? And so that is any number that ends in a 0. Well, that is equal to just 10A because B itself is 0. If we square that, if we take 10A and we square it, what we get is 100A squared. And another way of thinking about that would be like putting the A squared in the first position and then following it with 2 zeros, right? Now this might be more than one digit, right? Might be 2 digits. It can't be any more than that because the biggest A can be is 9. 9 squared is 81, which is still a 2-digit number, okay? But this pretty quickly allows us to identify the cases that satisfy, right? Since the only cases that satisfied all the digits less than or equal to 4 for a 1-digit number were 1 and 2, the only results that we're going to get here are 10 and 20, okay? And then we can repeat this process with some other trailing digits, right? So A1 would be the next case. If we expand that, that's 10A plus 1, so it's a multiple of 10 plus 1. And so we're going to square that, 10A plus 1 quantity squared. And remember that when you square something, you're not just squaring the terms inside the parentheses, you're multiplying 10A plus 1 by itself 2 times, right? So we'll get 100A squared, we'll get a plus 20A in the middle, and then a trailing 1, kind of as we expected to get, because 1 squared is 1. So what we expected, right? Any number that ends in 1 when you square it is also going to end in 1. And so what we can do is we can then rewrite this as A squared, and then notice that this 20A, that's going to show up in our tens place, right? Because it's 20s, so that's kind of the same order of magnitude. And so I'm going to put 2A in the middle there and a 1. So I'm kind of abusing notation here. This is the second digit, the tens place digit. It may carry into the leading digit, and then A squared also there's a good chance that it's more than 1 digit, right? But in general, this is the form that it's going to take. And now we're in a situation where we want 2A to be in a specific set of numbers. And we know that it has to be even, because anytime you multiply by 2, we get an even number. So 2A has to be 0, 2, or 4. Okay? And this isn't that complicated of a case. We're only looking at the digits between 0 and 9, and so we can pretty quickly identify that that's 0, 1, 2, as well as 5, 6, and 7, right? But let's talk a little bit about a more thorough or a more clean way to approach that. And I mentioned that we would talk about modular arithmetic. Modular arithmetic is basically a fancy way of talking about remainders, right? So the remainder of 12 divided by 5 is 2, and so we say 12 is equivalent to 2 mod 5. And so we're going to use modular arithmetic to explore the cases that might be interesting to us, right? So we're looking for things modulo 10 in our case, because modulo 10 just means that the last digit is going to be that certain number, okay? So we're looking for the cases modulo 10 where the values are less than or equal to 4, and because in this case it was a 2, we knew it could be an even number, right? Then we also want to talk about our thresholds, though, when we're thinking about the cases of trailing 1, right? So there were 2 cases. We only really focused on the larger of the 2 cases, okay? But you'll notice that if I take a 2-digit number squared, so if I take that expression squared, it's going to either be some number, we'll say it's a 3-digit number, so it's going to be like a CDE, or it's going to be a 4-digit number, CDEF. In this case, it has to be on the interval in between 100 and 444 would be the biggest possible number, okay? And we can say that it could include those endpoints. Again, kind of abusing notation here because we're not talking about numbers in between the integers, we're just talking about the integers, but that's okay. If it's a 4-digit number, it's going to have to be in between 1,000 and 4,444, okay? And so if we're looking at the range of values that fall into that, well, if we take the square root, okay, we can actually find the range of 2-digit numbers that form this range of 3-digit numbers. Well, 10 squared gives us 100, so that one falls on exactly. And it turns out that 21 squared is the largest square that is less than 444. And similarly, we can do the same thing here. It looks like the interval that we're dealing with is 32 to 66. And you might be curious where those numbers come from. You might notice some interesting elements about those numbers if you've fiddled around with numbers a good bit before. It's not a coincidence that this 66 is a little bit less than the decimal expansion of 2/3. And I'm actually thinking about making an entire video dedicated to why that's the case. It has some interesting properties related to repeated decimals. So if you've ever messed around with, for example, what is 2 over 3? It's 0.66666. If you square that, it turns out to be related to 0.44444. And that's not a coincidence. We can kind of show how that comes out of the fractions and all that. So maybe we'll dig into that at some point. So based on our modular arithmetic, we had identified for our case of a bar 1, right? We had identified that we were going to be looking at a leading 0, 1, or 2. Well, a 0 is a one-digit number. So 11, 21, and then 5, 6, or 7. Well, 11 and 21 fall into these intervals, so those are safe. And then 5, 6, and 7, well, the 7 case is eliminated by this upper bound, so these are the ones that we need to check. And it turns out that 11 squared and 21 squared do satisfy our condition, but that 51 and 61 do not. Okay, and so far we've identified 10 and 20 and 11 and 21 as the cases that give us all digits less than or equal to 4. Okay, we can do similar analysis with a bar 2, and the result out of a bar 2, just from my own experimentation, is 12 and 32. From a bar 8, we actually start to come across some more interesting cases. Well, actually 32 is interesting, right? Because 3 squared is 9. And so it actually turns out that some of the carrying from the 2 that's trailing pushes us above 1,000, which is, you notice that's the lowest end of this 32 to 66 interval, right? And so we're in that particular scenario, that's where that 32 arises. A bar 8 spits out a couple of values as well. It spits out 18, 38, and 48. So we have another interesting pair of cases in this case. Both 38 and 48, some of the carrying allows for all the digits to be less than a certain number. In this case, 4 or less. And in the case of a bar 9, 49 is the only case that comes out there. So we actually ended up with 4 numbers here where, or maybe 5, where I would say it's kind of like a not trivial result, right? So if you think about 10, 11, 20, and 21, those are kind of boring, 12 as well, because each of those digits squared they're all numbers less than or equal to 4. So in the other cases here, 32, 18, 38, 48, 49, we had some sort of simplifying process, right? Because those numbers contain digits that individually do not square to a number less than or equal to 4, but when combined with another digit, we did get a result that was less than or equal to 4. Okay, now let's talk about 3-digit numbers, and the cases here start to be enormous, because not only could we trail behind any of the numbers that we counted in the 2-digit case with a 0, all of those would then just be the same as the square of the 2-digit number with 2 zeros tacked onto the end once you square it. We also might come up with a bunch of other cases where just kind of a combination of coincidences results in all of the digits being less than or equal to 4. So for the case of 3-digit numbers, I'm going to restrict us to the case where the largest the digit can be is 3, okay? And so that actually eliminates the cases that have a trailing 2, because 2 squared is 4. That last digit is a 4, and similarly with 8 squared was 64, and so the last digit would be a 4. And so all we need to look at for the cases of A, B, C, well, we need to look at the cases A, B, 0, A, B, 1, and A, B, 9. So let's square this first term. That's 100A plus 10B, quantity squared. That's going to spit out, and this is going to be a little bit messier because we're going to have to use expressions in order to define our digits. Okay, so the trailing zeros you would probably expect, okay? And this a squared, 2ab, b squared looks sort of like expanding a binomial, if you've come across that before in an algebra context, okay? And so what I'm saying here is I'm saying that the leading digit is this a squared, which might be more than one digit, that there's a 2ab digit in the middle, and then following that is a b squared digit, both of which might also carry to the place in front of them. And if you do a little bit of casework here, well, a has to be 1, 0, or 9. It can't be 0 because then it's not a 3-digit number. It can't be 9 because then the leading digit would be way too big. So remember we had this range of values, right? In the case of 3 digits, it's going to be between 100 and 210 for squaring and creating a 5-digit number. And to square and create a 6-digit number, it's going to have to be in between 317 and 666. So basically that leading 9 case would just be way too big for your leading digit to be a 4 or smaller, or a 3 or smaller in the case that we're looking at here. So these ranges would actually be even more narrow than that, than they were for the 4-digit case. And so the leading digit is going to have to be a 1. You do a little bit of casework on B, and you find that the only values here are 100 and 110. Not terribly interesting, sort of like the 10, 11, 12, 20, 21 results we found for 2-digit numbers. In the case of AB1, so if we take this and we square it, we get 100A plus 10B plus 1. That's just expanding the AB1 digits, okay? When we expand this, we get an even uglier result, okay? It is an A squared in the leading position, followed by a 2AB, sort of similar to what we had up above, and then it gets even worse. We have 2A plus B squared in the hundreds place, and then we have 2B, and then we end with a trailing 1, again, as we expect, because when we square a number that ends in 1, we should expect that that number ends in 1. And so from here, what we're going to do is we're going to do some casework, and we want to stay in these intervals, okay, and actually, like I said, slightly narrower than these intervals. And so what we're going to look at is we're going to look at cases probably where the B doesn't break the 2B here being a digit bigger than 3. So based on our modular arithmetic conversation, we know that that B is going to have to be a 0, a 1, a 5, or a 6. And so we could check all 4 of those cases kind of within this case. And the end result here is, somewhat unsurprisingly, we get 101 and 111. We also, though, get our first 2 interesting 3-digit cases, 351 and 361. I sort of spoiled this a little bit. The thumbnail had 351 as an example. But these are really surprising, right? 3 and 5 squared definitely don't individually, or 6, have their digits all be 3 or less. But when we square them, we end up with a result that has all of its digits being the value of 3 or less. You do similar casework on AB9. You end up with a little bit more carrying because 9 squared is 81, so there ends up being this extra 8 in the ones place. But other than that, it looks really similar. And the end result in this case is that we only get the value of 149. So again, that's another interesting one. I think 149 is particularly interesting, actually, because 149 squared is 22,201. All of the digits actually are 2 or less, so we don't even have any 3s showing up in that particular case. So where do we go from here, right? Well, we can certainly explore 4 digits, 5 digits. Maybe we expand our constraint back up to 4, or we shrink it down to 2 and see if we can happen to find any 4 or 5-digit numbers that square and all of the digits are 2 or less, kind of like 149 is in the case of a 3-digit number. And I mentioned we would talk about entropy. You notice that when we were dealing with 3-digit numbers, we were 5 and 6 digits. Similarly, if we talk about 4-digit numbers, we're talking about their squares being 7 and 8 digits. And so what you notice is that each digit in our number that we're squaring is responsible roughly for 2 digits in its square. And so we start to see that meeting these kinds of criteria gets more and more complicated. And so one of the things is kind of a extension to this problem is, I think a great thing to explore would be numbers that look like they're binary, so just strings of 1s and 0s. Because when you square those, you mostly get just copies of 1s and 0s, right? Because 1 squared is 1 and 0 squared is 0. And then there's some sort of interaction between the digits, only in specific cases. And so you want to look for ways to not have too many of those digits overlap. So for example, 111 squared is 1, 2, 3, 2, 1. 1,111 squared is 1, 2, 3, 4, 3, 2, 1. And so we would crack that 4 threshold. Maybe we're interested in exploring not cracking the 3 threshold. Probably a good first problem to explore would be, what binary looking numbers can you square and not have any of the digits exceed a 2, just because there's less casework to do there. All right. Hope you found this interesting. If you have any questions, as always, don't hesitate to reach out.